So last class we talked about what a function is, and we learned its definition, right? It was that for each input there's exactly one output. It's just a rule where each input has exactly one output. And we learned some notation associated with it. And so today we're going to learn some more vocabulary associated with functions. So the first is domain and range. The domain of f is the set of all possible input values for which the function makes sense. So we have found domains before, right? We have been finding the domain of an expression. And so up until this class, we have been finding domains of functions. We just didn't know the word function. Okay, so this isn't really new, the domain part. The range is a little bit new. That's the set of all output values of the function. So if you think of the function like a machine, right? The domain is all the things that you're allowed to drop into the top of the machine that won't jam the machine, right? And the range is all the things that the machine creates, all the things that come out of the machine. So if this is my rule, where I input x, and f is the rule that determines the name of x's biological mother, first of all, how do I know this rule is a function? You get only one answer because every person has exactly one biological mother, right? So we know it's a function. So I'm just going to put these down. We know it's a function because every person has exactly one biological mother. So the domain of a function is the set of all inputs. So what things do we put into this function machine? What is the set of things that can go in there? X, and what does X represent? No. The child, yeah, the names of people, right? The names of people. So then the function gives you the name of the biological mother. So the input is the domain, is the set of all people. You can put any person into the function machine because every person has a biological mother, right? So you can put in the name of anyone, and it's not going to jam the machine. It makes sense to ask for the name of their mother, right? The range of this function is what? The things that the function produces. Biological mother. So the range of this function is the set of all biological mothers. So it's not the set of all people, right? Because not all people are biological mothers. The set of outputs for this function is just biological mothers. So that's called the range. So now we're going to do one that's just a little more theoretical. So we're going to find the domain and range of this function that I have graphed here. And remember, x is generally your input axis. Y is generally your output axis. So when I ask for domain, I'm asking for all of the x values that produce a function value. All of the x values that have a y. So if I just look at this little piece to start with, and before we start, I'm going to say all of these circles are filled in. It's just the computer program I made likes to have open dots, but imagine they're all filled in. So just look at this little chunk here, this ABC piece. I want to know what x values does it live on? What's the smallest x value and the biggest x value where that function lives. 2 to 6, yep. So we can just drop down to the x-axis. And we've got here are x values where that function lives, from 2 to 6. Okay. Now, how about the other piece of the graph? What x values does that piece live on? 7 to 11, 12, 13, 14, 15. 7 to 15. Okay, so my domain is the set of x values where the function lives. So my domain here is going to be 2 to 6 unioned with 7 to 15. So that's the set where my function lives, the set of x values. Now I'm going to find the set of y values where my function lives, because that's my range. So for this little piece up here, this A to C part, what's the smallest y value and the biggest y value? 4 to 6. So we just go over to the left and we say, well, this piece of my graph, it lives on y values from 4 to 6. And then this other curvy part, the smallest y value is down here. Looks like, I don't know, negative 1.8. And then where's the biggest y value? 2.2. I'm going to go to the highest point on the graph. 2.2, 2.3, I don't know, it's an estimate. And then my function lives on those y values. So the range is going to be negative 1.8 to 2.2, unioned with 4 to 6. And I have a fun little animation of what we just did that helps, I think, visualizing domain and range. Same graph as before, I'm going to show the domain. And it highlights all the x values where the function lives, from 4 to 6 and 7 to 15. And then if I show the range, it shows all the y values where the function lives. Negative 2 to 2.2 and 4 to 6. All right, so sometimes a domain is given explicitly, which means they just tell you. Okay, you read the problem and they just tell you exactly what the domain is. So for example, if they say f of t equals negative 16t squared minus 48t, and then they put comma and t is sandwiched between 0 and 4, they're just telling you the domain, 0 to 4. Right? Those are the t values that make sense for this function. Or those are the t values for which they're defining the function. So sometimes they'll just come right out and tell you. Right after the formula, they give you the domain. Sometimes you have to infer it from a word problem. So the American Medical Association has this formula for the number of doctors in the private sector in year X. And so you plug in X for the year and it tells you the number of doctors, right? But then they tell you that you can only plug in values from 1970 to 2000. You can only plug in years from 1970 to 2000. Otherwise, maybe this model is inaccurate. Maybe there's a big jump in doctors after 2000 or a decline, I don't know. But the domain was given to us in the problem, 1970 to 2000. So sometimes they just give us the domain and make it easy on us. Sometimes the domain is implied, which means just all the values that the function makes sense for. So if I have a square root, I have to make sure that I never let the thing under the square root be what? Negative. So I just have to make sure that x minus 2 is never negative. It's always bigger than or equal to 0, which means that x has to be bigger than or equal to 2. That's my domain, 2 to infinity. All the x values that make sense. So if we think of this like a function machine, if I plug in any of these values, I'm fine. The function machine cranks out an output. If I try to put in something smaller than 2, like say I try to put in a 0, I drop a 0 into this function machine, it does 0 minus 2, it tries to square root, and I jammed the machine, right? So I can't put that one in. It's not part of the domain. So the range for this function, when you're given a formula and you want to find the range, sometimes you can think it through and figure out what kind of outputs it makes, and sometimes that can be tricky. So I'm going to show you how to do it by looking at a graph, because just a couple minutes ago we found domains by looking at a graph and it wasn't too hard. So we can do that because we have the technology to take a formula and turn it into a graph. So I want to look at a graph of the square root of x minus 2. And I'll just start with the standard window, zoom 6. And it looks like I don't need a lot of the stuff on the left or down below the x-axis. So I'm going to change my window a little bit. Maybe I'll do like -2, -2 to 20, and -2 to 20. All right, so that looks pretty good, although maybe I don't need to go quite so high for y max. Just go to, that's better. All right, so we can see the domain in this picture. We already figured it out algebraically, but you can see the domain starts here and goes to infinity. So this is where my function lives, from 2 to infinity for x. Where does this function live for y? What's the smallest y value? 0. Yeah. Smallest y value is 0. And then this function, does it level off? Does it come back down? Does it keep going up? It keeps going up. Yeah. So it lives on y values from 0 to infinity. And the domain we could see graphically also to infinity. So that's something you can always turn to. If you don't know how to find the domain algebraically, make a graph. All right, so remember the definition of a function is that each input creates exactly one input. So does this graph represent a function? Are there any inputs that give more than one output? What's one? Yep, so if I look at the input of 2, I have an output of 5 and an output of -1/3, something like that. Or if I put in 4 as my input, I have 2 different outputs, one at 5, one at -1, right? So I have some inputs that are giving me more than one output. That makes this not a function. it only has to happen once, one time. If there's one input that has more than one output, the whole thing's not a function. Because there are x values, inputs, with more than one y value or output. So this leads us to a handy little shortcut for checking whether a graph is that of a function called the vertical line test. So what made this not a function is that at 4, there were 2 different outputs. So if you draw the line, a vertical line through 4, it touches the graph in 2 places because there are 2 different outputs. So the vertical line test says that if you can draw a line that intersects the graph more than once, if you can draw any vertical line that intersects the graph more than once, then it is not a function. So let's go through these. Which of these is a function? First one's a function. I can draw any vertical line anywhere, never touches the graph more than once. So that one's a function. How about the second one is also a function? How about the third one? Nope. There are lots of places where I can draw a vertical line. It intersects twice. Not a function. How about the circle? Nope. Lots of places again. How about this function that's defined in 2 different pieces here? I shouldn't have called it a function, right? It's not, because there's one vertical line that if I draw, it's going to intersect the graph in 2 places. So that one's not a function. Even though it's just one spot, it's not, the whole thing's not a function. But then in this next picture, I fixed it, right? I made one of these dots open. So now when I draw a vertical line here, it only touches in one spot. So that one is a function. Okay, so a little more vocabulary associated with functions. Functions can be increasing, decreasing, or constant over an interval. And we say that it is increasing if the y values get bigger as the x values get bigger. It's constant if the y values stay the same. And it's decreasing if the y values get smaller as the x values get bigger. So you can think of it as reading the graph from left to right. Okay? If you read from left to right, just like we normally read, if the function is going downhill, it's decreasing, constant, it's constant, and if you're going uphill, it's increasing. And when you're saying where a function is increasing and decreasing, you only ever give x values. So when I look at this picture, I would say this function is decreasing on the interval from a to b. And I'd only give x values. It doesn't matter at all what the y values of those 2 points are. You just give the x's. Because it's a function. So if I tell you the x's, you could figure out the y's, because there is exactly one y paired to every x. Also, there's always a question about whether to use square brackets or round brackets when you give the interval of increasing and decreasing. Our textbook always uses square brackets, but this is just a convention of our textbook. Some textbooks will always use round, because there's an argument to be made for either one, right? That at this point right here, you know, it's neither decreasing nor constant, or it's both. So always use square brackets like when you're in WebAssign, because that's what our book does, but know that that's not a totally accepted convention. Yes. Yes. No, for both, for both. Yeah, so I would say this function is increasing on the interval c to d. So in your groups, determine the intervals on which each function is increasing, decreasing, or constant. So you got 2 here. Remember, X values only. Okay, so let's start with decreasing. So this function is decreasing. You read it from left to right. It's decreasing when you're going downhill. So from this point to this point, the function's decreasing, right? The way you give locations, if you're dealing with a function, you only give the x as the location because it's assumed that the reader could figure out the y if they wanted to, because it's a function. So each y has each x has one y associated with it. So I only have to give x values. So I would say it's decreasing from -4 to 2. I just give the x values from here to here. X values where I'm decreasing, -4 to 2. And then I want to give x values where the function is increasing. Again, smallest to biggest, left to right. So this arrow indicates that it goes down and left forever. So I would say -infinity to -4. And still use round brackets on infinities. That stays the same. And then I start increasing again when x gets to 2. So from 2 to 5. So from x equals 2 to x equals 5, function's going uphill again. And is there anywhere that this function is constant? No. So a couple of ways of saying the set that has no numbers in it is that, the empty set, or little braces with nothing in between. You could just write none. All right, let's look at one more. So this function, let's start with decreasing. So it looks like it's decreasing from -infinity all the way until when? -3. Good. So -infinity to -3. Does it ever decrease again? Yes, starting where? At 4, because we just give x values, and then it goes on for forever. And then increasing from where to where? Where the function, if you're reading from left to right, the function has to be going uphill, -3 to 0. And that's the only place. And then we're constant from where to where? 0 to 4. Very good. All right, so related to increasing and decreasing is the idea of a maximum or a minimum point. So we're going to talk about local maximums and local minimums, which means that they're not necessarily the very highest or very lowest point in the whole graph. They're just the highest or lowest point in their neighborhood. So like right here, that point right there, it's not the highest point in the whole graph, but if I make a little neighborhood around it, it's the highest point in its neighborhood. So that's what it means to be a local maximum or local minimum. Now there's some very specific vocabulary in the way, not even vocabulary, like syntax in the way you talk about the local maximum value and where it happens. Okay. So the maximum value is the y value. It's located at the x value. So x values are generally locations. Like here, when I ask, determine the intervals where, right, or in which the function is decreasing or increasing. X values are locations. They're like addresses. And then the y value is the actual maximum value of the function, or minimum value of the function. So for example, this guy has a local maximum right here, right? That highest point. Its maximum value, the function has a maximum value of, and then you give the y coordinate. So the y coordinate of this point would be, it looks like it's hard to tell from the graph, but we could figure it out because we have the formula, right? What's the x coordinate at this point? 0. So if I plug 0 into the formula, I get 4. Yep. So this function has a maximum value of 4 at x equals 0. So you have to just pay very careful attention to what they ask for. So if the question says, what is the local maximum value of the function, you would say 4, right? If they ask for the maximum or minimum value, you give the y coordinate. If they ask for the location, where does the local maximum or minimum occur, you give the x value. So here's one. What is the local minimum value for this function? 0. And it occurs at x equals 2. So here, the local minimum value of the function is 0. That's the lowest the function goes, is y equals 0. It occurs at an x value of 2. So how about this one? Does it have a local maximum or minimum anywhere? No. So these keep going forever because it's x cubed. So it's always going up to the right, always going down to the left. The only interesting point is that one at 0, 0, but it's not the highest or lowest point in its neighborhood. So there's no local extrema. So extrema is just the word that encompasses maximums and minimums. Okay. There are no maximums and no minimums, so there are no extrema. Okay, so this question, we have a few minutes, so we can do part of it anyway. All right, so we have a highway engineer. He wants to estimate the maximum number of cars that can safely travel a particular highway at a given speed. So she's going to assume that each car is 17 feet long, travels at a speed of s. So s is a variable that can change, right? Because cars can travel at various speeds. And she's going to also assume a safe following distance for given speeds. May or may not be a useful assumption. She's going to assume that people do that. Okay. So she comes up with this formula that finds the number of cars that can pass a given point per minute is given by this function. So she found this formula by like standing on the side of the road and counting how many cars passed her. Right? And figured out that this is the formula for the number of cars that will pass her in a minute, where s is the variable at differing speeds. So let's look at a graph of this function. So we have to be careful when we're entering it with parentheses because we get a fraction. So we need parentheses around the whole top and the whole bottom. So we want 88, and I'm using x because I don't have an s variable key, so I'll just use x, divided by 17 plus 17 times x over 19 squared, close the parentheses. So because this is a word problem, I'm going to use it to help me figure out what the window should be. So remember, S is representing the speed that cars are driving along the highway. So what's the lowest speed that would make sense? 0. I mean, people wouldn't drive at 0, but they could drive real close to 0. And what would a really fast speed be? 80? Sure. And we're trying to study safety. So I mean, maybe we'd be interested in what happens if somebody, goes crazy and is driving like a maniac, right? Okay, and then Y represents the number of cars that pass her in a minute. So if nobody's moving, how many cars are going to pass her in a minute? 0. Nobody's going to drive by, right? And as cars start, what would a lot of cars to pass you in a minute be? If you were standing there holding a stopwatch and counting the cars that go by, what would a lot be? 60, like 1 per second? That would be pretty quick. So let's go Y max is 60. And we'll graph it. That's a pretty decent window. We got a nice, good picture of the graph. So let's talk about why the graph looks like this. So remember, this is speed, and this is the number of cars that passes per minute. So when speed is 0, no cars pass per minute, right? And then as we speed up, more and more cars go by every minute, right? That kind of makes sense, right? As cars go faster, they're going to pass you faster. Okay, but then we reach a maximum value here. And then as we pass this critical speed, whatever this speed is, I'm putting S sub C for critical speed, then the number of cars that pass us starts to slow down. Fewer cars go by every minute. Why is that? Yes, because the distance between them is greater, right? Because the faster you drive, the further the safe following distance is. And we have assumed that people are going to obey safe following distance, even though we're also assuming they might drive 100 miles per hour. So why they would follow one rule and not the other, I don't know, but that's what happens. We're assuming safe following distance. So at some critical speed, the following distance gets so big that it actually means fewer cars will go by you in a minute. All right, so I think that that's good. Some of your homework questions are about interpreting things like this. So the important thing is to be able to use the problem to make a good window, right? To think about what values of input and output make sense. And then you might have to answer questions about domain and range and this maximum point. Oh, I should show you how to find that maximum point. That's important. Your calculator can tell you exactly where it is. It's in the calculate menu. Option 4 is maximum. And if you're looking for a minimum, it's option 3. And you use it almost just like 0. You do left bound, right bound, guess. So you just move the cursor till it is somewhere to the left of this maximum. And then move it so it's somewhere to the right of the maximum. Hit enter. And then guess. Somewhere between your left bound and your right bound. And it says that that maximum value happens at 19,49 if I'm rounding to the nearest whole number. So 19, what does that represent? What are the units on that 19? Speed, yes. It's an input, right? It's the x value. X-axis is speed. So 19 represents miles per hour. So this is 19 miles per hour, comma 49. And what are the units on that one? cars per minute. So we know that the maximum number of cars per minute that can pass is 49. It happens when speed is 19 miles per hour. So units can really help you when you're doing questions that ask you to interpret things. Always write down the units and it will like just make everything clear.